From space, Earth looks like a blue marble. And for good reason. Roughly 71% of the surface is covered in water. That surface area equates to an estimated 1.33 billion cubic kilometers of water. It is a staggering, almost incomprehensible volume of liquid. Yet, despite this abundance, the United Nations repeatedly warns that humanity is facing a severe, accelerating water crisis. How exactly does that work? How can a planet practically drowning in water run out of it? To find the answer, we have to look at the math. If we take every drop of water on Earth, 100% of our supply, and strip away everything we biologically or physically cannot use, we get a much clearer picture of what we actually have. First, we have to isolate the largest reserve on the planet. 97% of Earth's water is held within our 5 oceans. The sheer physical scale here is massive. The average depth across these oceans is 2.7 kilometers. But there is a chemical barrier to all of this. Every liter of seawater contains an average of 35 grams of dissolved salt. Human kidneys simply cannot process that level of salinity. If you try to drink it, your body actually uses up more of its own water trying to flush out the salt, accelerating dehydration. So while the ocean acts as the vital engine of our global water cycle through evaporation and rain, its chemistry entirely disqualifies it as a direct source of drinking water. That leaves us with a tiny 3% sliver. This is all the fresh water available for terrestrial life. But we lose a huge portion of this to a physical filter. Roughly 69% of this fresh water is locked away as ice, specifically in the massive ice sheets of Antarctica and Greenland. These ice caps naturally function as the planet's water towers, safely storing and slowly releasing fresh water into the environment over long periods of time. As global temperatures rise, this ice melts faster. The runoff flows directly into the oceans, mixing with the brine and turning our stored fresh water into salt water. Once we subtract the ice, we hit a geographic filter. About 30% of the remaining non-frozen fresh water is trapped deep underground in subterranean aquifers. By the time we look at the surface, the rivers, lakes, and swamps we can easily reach, we are left with less than 1% of the global freshwater supply. When you run the final calculation, filtering out the salt, the ice, and the deep underground rock, the easily accessible drinking supply for all of humanity is roughly 0.3% of Earth's total water. Let's scale down from planetary geology to our own biology. A human body is roughly 60% water. Maintaining that balance carries a strict biological cost. An adult needs to consume about 2 to 3 liters of water every single day. The system is incredibly fragile. A drop in bodily hydration of just 2% triggers distinct physical fatigue and cognitive decline. That microscopic 0.3% global supply is the entire foundation for our survival. It drives our agriculture, our industry, and our daily biological needs. Earth is covered in water, but the vast majority of it is either toxic to our kidneys or locked away in ice. Protecting the tiny, accessible fraction we have left is a strict biological imperative.